Good morning and welcome to our first lecture on statistical mechanics. We will introduce the subject today and we'll make a reference from classical mechanics to quantum mechanics and then to statistical mechanics. Classical mechanics is a physical theory describing the motion of macroscopic objects from projectiles to parts of machinery and astronomical objects such as spacecraft, planets, stars, and galaxies. For objects governed by classical mechanics, if the present state is known, it is possible to predict how it will move in the future and how it has moved in the past. The earliest development of classical mechanics is often referred to as Newtonian mechanics, as it consists of the physical concepts based on foundational works of Sir Isaac Newton and the mathematical methods invented by Gottfried Wilhelm Leibniz, Joseph Louis Lagrange, Leonhard Euler, and other contemporaries in the 17th century to describe the motion of bodies under the influence of a system of forces. Later, more abstract methods were developed, which led to the reformulations of classical mechanics known as Lagrangian mechanics and Hamiltonian mechanics. These advances, made predominantly in the 18th and 19th centuries, extend substantially beyond earlier works, particularly through their use of analytical mechanics. They are, with some modification, also used in all areas of modern physics. Classical mechanics provides extremely accurate results when studying large objects that are not extremely massive and speeds not approaching the speed of light. When the objects being examined have about the size of an atom diameter, it becomes necessary to introduce the other major subfield of mechanics, which we call quantum mechanics. To describe velocities that are not small compared to the speed of light, special relativity is needed. In cases where objects become extremely massive, general relativity becomes applicable. However, a number of modern sources do include relativistic mechanics in classical physics, which in their view represents classical mechanics in its most developed and accurate form. Statistical mechanics is the branch of physics that combines the principles and procedures of statistics with the laws of both classical and quantum mechanics, particularly with respect to the field of thermodynamics. It aims to predict and explain the measurable properties of macroscopic systems on the basis of the properties and behavior of the microscopic constituents of the system. Statistical mechanics interprets, for example, thermal energy as the energy of atomic particles in disordered states and temperature as a quantitative measure of how energy is shared among such particles. Statistical mechanics draws heavily on the laws of probability so that it does not concentrate on the behavior of every individual particle in a macroscopic substance, but on the average behavior of a large number of particles of the same kind. So, statistical mechanics is the branch of theoretical physics that attempts to predict, by starting at the level of atoms, molecules, spins, or other small particles, the bulk properties of systems in which a large number of these particles interact with one another. In other words, it links the microscopic properties of matter, that is, molecular interactions and structure, as determined from the laws of quantum or classical mechanics, to its macroscopic properties, for example, pressure of a liquid. The province of statistical physics is more general. extending to any situation in which one is interested in the collective behavior or interacting entities from population dynamics through solids, liquids, and gases to cosmology as well as random heterogeneous materials. Systems composed of many interacting particles, albeit much larger than molecular dimensions, are often useful models of random heterogeneous materials, and thus one can exploit the powerful machinery of statistical mechanics to study such materials. Moreover, as we will see in the subsequent subsequent lectures, the formalism of statistical mechanics can be extended to non-particulate systems. Statistical physics explains and quantitatively describes superconductivity, superfluidity, turbulence, collective phenomena in solids and plasma, and the structural features of liquid. It underlies the modern astrophysics. In solid-state physics, statistical physics aids the study of liquid crystals, phase transformations, and critical phenomena. Many experimental studies of matter are entirely based on the statistical description of a system. These include the scattering of cold neutrons, X-ray, visible light, and more. Statistical physics also plays a role in material science, nuclear physics, astrophysics, chemistry, biology, and medicine. That is, the study of the spread of infectious diseases. In the history of development of thermal physics, the 50s of the 19th century mark a conspicuously important period. The science of thermodynamics grew essentially out of an experimental study of macroscopic behavior of physical systems, but the original works by Carnot, Joule, Clausius, and Kelvin transformed it into a secure and stable discipline of physics. The theoretical conclusions drawn from the first two laws of thermodynamics were found to be in excellent agreement with the experimental results. The kinetic theory of gases tried to explain the macroscopic properties of gaseous systems in terms of the motion of the molecules. The theory had so far relied more on speculation than calculation, but by this time it started emerging as a real mathematical theory. The initial successes of the theory were astounding. However, a real contact with the thermodynamics could not be made until about 1872, the year in which Boltzmann developed his H theorem, whence he could establish a direct connection between entropy and molecular dynamics. Almost simultaneously, the kinetic theory began giving way to its more sophisticated successor, the ensemble theory. The power of the technique that finally emerged reduced thermodynamics to a status of an essential consequence of the get-together of the statistics and mechanics of the molecules constituting a given physical system. It was then natural to give the resulting formalism the name statistical mechanics. One may wonder, why do we need statistical mechanics when we have already classical mechanics and quantum mechanics, which deals with different systems? Why do we need statistical mechanics? So as we have seen, when we go to systems which consist of atomic or subatomic particles, the formalism which were developed for classical mechanics did not work. So we had to develop a different kind of mathematics to deal with such systems, which we call quantum systems. Now, the method that we have learned in classical mechanics is that if we have a system of 4, 5, 6, 10 bodies, whatever be the number, we write equation of motion for each body and then solve it by knowing the initial conditions. Similarly, in quantum mechanics also, we write equation of motion, the Schrodinger equations are required, and then we try to solve it. Now, if we have a system with very large number of particles, then the same method will be applied, that we will write equation of motion for each body or each particle and then try to solve it with known initial conditions. Suppose we have a system of 1 mole of a gas. So the number of particles involved there will be 6.023 10 to the power 23. So these many molecules are there, which means if we adopt that classical method, we'll have to write these many equations and then solve those equations if we know the initial conditions. One can see it is almost an impossible job even if we use supercomputers. So obviously for the systems which consist of very large number of particles, the methods that we have learned in classical mechanics and in quantum mechanics are not going to work. So we have to develop a different kind of method, and that is what statistical mechanics is, which doesn't aim at describing the motion of individual constituents of the system, but it aims at describing the macroscopic properties of the system as a whole. Let's discuss macroscopic and microscopic states of a system. Suppose we consider a physical system composed of N, capital N, identical particles confined to a space of volume V. In a typical case, N would be an extremely large number, generally of the order 10 to the power 23. In view of this, it is customary to carry out analysis in the so-called thermodynamic limit. Thermodynamic limit. Which is when n tends to infinity and v tends to infinity in such a way that the ratio n to v, which represents the particle density, stays fixed at a pre-assigned value. So this remains constant. So when this condition is satisfied, that n tends to infinity and v tends to infinity in such a way that n by v remains constant, we say we are in thermodynamic limit. In this limit, the extensive properties of the system becomes directly proportional to the size of the system. That means it is proportional to n or v. But the intensive properties, they become independent of these quantities, of this n or v. The particle density remains an important parameter of all physical properties of the system. Now further, if the particles comprising of the system could be regarded as non-interacting, then the total energy E would be equal to the sum of energies epsilon I of the individual particles, which means E will be sum over I Ni epsilon I, where Ni is the number of particles with energy epsilon I, and the sum will be the total energy capital E. Obviously, this means capital N, which is the total number of particles, will be sum over I and I. According to quantum mechanics, the single particle energy epsilon I are discrete and their values depend critically on the volume V to which the particles are confined. Accordingly, the possible values of total energy E are also discrete. However, for large volume V, the spacing of different energy values is so small in comparison with the total energy of the system that the parameter capital E may well be regarded as a continuous variable. This would be true even if the particles were mutually interacting. Of course, in that case, the total energy E cannot be written in the above form. Thus, the specification of actual values of the parameters capital N, which is the total number of particles, capital V, which is the volume where the particles are contained, and capital E, which is the total energy of the system, then defines a macro state of the given system. So, the specification of the actual values of the parameters N, V and E then defines a macro state of the given system. At the molecular level, however, a large number of possibilities still exist because at that level there will in general be a large number of different ways in which the macro state, which is defined by N, V and E of the given system, can be realized. In the case of a non-interacting system, since the total energy capital E consists of a simple sum of n single particle energies epsilon I, there will obviously be a large number of different ways in which the individual epsilon I can be chosen so as to make the total energy equal to capital E. In other words, there will be a large number of different ways in which the total energy capital E can be distributed among the n particles constituting it. Each of these different ways specifies a microstate or complexion of the given system. In general, the various microstates or complexions of a given system can be identified with the independent solutions psi R1 to Rn of the Schrödinger equation of the system corresponding to eigenvalue E of the relevant Hamiltonian. In any case, to a given macro state of a system, there does in general correspond a large number of microstates, and it seems natural to assume that when there are no other constraints, at any time t, the system is equally likely to be in any one of these microstates. This assumption forms the backbone of our formalism and is generally referred to as the postulate of equal a priori probabilities. So, equal a priori probabilities. So, the assumption that at any time t, the system is equally likely to be in any one of the microstates available to it forms the backbone of our formalism, and this is generally referred to as the postulate of equal a priori probability for all microstates consistent with the given macrostate. The actual number of all possible microstates will, of course, be a function of n, that is capital N, total number of particles, V the volume and energy E, and it may be denoted by a symbol omega, which is a function of N, V and E. So omega is the total number of microstates corresponding to a particular macrostate of the system, and that is a function of N, V and E. The dependence on V comes in because the possible values epsilon I of the single particle energy are themselves a function of this parameter, that is volume. It is remarkable that it is from the magnitude of the number omega and from its dependence on the parameters N, V and E that complete thermodynamics of the system can be derived. And that is what we will be doing in our coming lectures. Let's discuss contact between statistics and thermodynamics, which will show the physical significance of this number omega, which is a function of N, V and E. Let's consider two physical systems, A1 and A2, which are separately in equilibrium. Let the macrostates of A1 be represented by the parameters N1, V1 and E1, so that it has omega 1 possible microstates, and this number omega 1 will be, as we have mentioned earlier, a function of N1, V1 and E1. Similarly, let's take omega 2 as the number of microstates for system A2, and that will be a function of N2, V2 and E2. The mathematical form of the function omega 1 may not be the same as that of omega 2, because that ultimately depends upon the nature of the system. We do, of course, believe that all thermodynamic properties of the system A1 and A2 can be derived from the functions omega 1 and omega 2 respectively. Let's take the first case, case 1, where we bring the two systems to thermal contact with each other, and thus we allow the possibility of exchange of energy between the two. This can be done by sliding in a conducting wall and removing the impervious one. For simplicity, the two systems are still separated by a rigid, impenetrable wall, so that the respective volumes V1 and V2 and respective particle numbers N1 and N2 remain fixed. Of course, total energy remains fixed, but E1 and E2 shall vary such that the total energy, let's say E naught, is equal to E1 plus E2. Let's denote the composite system A naught by A1 plus A2. To make the thing simpler, we neglect any interaction energy between the systems A1 and A2. As all the microstates omega 1 and omega 2 are equally probable for the systems A1 and A2 respectively, at any moment of time t, the composite system may be found in any of the microstates omega naught, where omega naught is given by, as it is function of E1 and E2, this will be omega 1, which is function of E1, into omega 2, which is function of E2. One can see that omega naught, which obviously is a function of E1 and E2, will not be the sum of omega 1 and omega 2. That will not be correct, because for each omega 1 there are omega 2 possibilities. So for each value of omega 1 rather, there will be omega 2 different possibilities. So the total number of microstates available for the system will be, as we have written, omega naught, and that will be function of E1, E2, which will be equal to omega 1 into omega 2. For each value of omega 1, there are omega 2 possibilities. We are writing number of microstates a function of energy only, because number of particles and volume remain fixed separately in system A1 and A2. As we can see from here, E2 will be E0 minus E1. So omega naught, which is function of E1 and E2, can be written as product of omega 1 function of E1 into omega 2, which is function of E0 minus E1. Thus omega naught can now be written as a function of E0, which is a constant, and E1. So that is equal to omega 1 E1 into omega 2 E0 minus E1. So now one can say that the value of omega naught, which is the number of microstates for the composite system, changes with varying E1. It becomes a function of E1 only. So it changes with varying E1 until at certain value of E1, the composite system reaches equilibrium. Now at this point we assert that when a system is left to itself, it proceeds in a direction that provides it larger number of microstates. I repeat, we assert at this point that when a system is left to itself, it proceeds in a direction that provides it larger number of microstates. The idea is that larger the number of microstates corresponding to a macrostate, more probable is that macrostate. So probability of a system to be present in a particular macrostate depends on the number of microstates available for that particular macrostate. So macrostate in which larger number of microstates are available is more probable macrostate for a system in equilibrium. So naturally, the exchange of energy between the systems shall continue until the composite system reaches a macrostate with maximum number of microstates. So that macrostate corresponding to which we have maximum number of microstates will be the macrostate for the system in equilibrium. Thus, most probable state of a system is the one in which the system spends an overwhelmingly large fraction of its time, and hence this state is identified as the equilibrium state of the system. The most probable macrostate of a system is the one in which the number of microstates is maximum. Let's say when the composite system reaches equilibrium, E1 bar is the amount of energy associated with the system A1, and E2 bar is the energy associated with system A2. Obviously, E1 bar plus E2 bar will be equal to the total energy E naught, because total energy remains the same, and that is also equal to E1 plus E2 as we have taken earlier. Now let's maximize omega, means omega naught. So we have taken omega naught, this function of E naught and E1, and that was equal to omega 1 E1 into omega 2 E2, where E2 we have written as E naught minus E1 earlier over here. So if you maximize it, we will write dou omega naught E naught E1 by dou E1 at E1 equal to E1 bar equal to 0, and that from the right hand side will be equal to dou omega 1 E1 by dou E1 at E1 equal to E1 bar into omega 2 E2 bar plus the second term omega 1 at E1 bar into dou omega 2 E2 by dou E1 at E1 equal to E1 bar. Now that can be written as dou omega 1 E1 by dou E1 at E1 equal to E1 bar into omega 2 at E2 bar plus omega 1 at E1 bar into dou omega 2 E2 by dou E2 at E2 equal to E2 bar into dou E2 by dou E1 equal to 0. But as E1 plus E2 is a constant, that is equal to E naught, and that is constant. So one can see that dou E2 by dou E1 will be minus 1, and when we substitute it over here, we obtain dou omega 1 E1 by dou E1 at E1 equal to E1 bar into omega 2 at E2 bar equal to omega 1 at E1 bar into dou omega 2 by dou E2 at E2 equal to E2 bar. We can rewrite this as 1 by omega 1 at E1 bar dou omega 1 E1 by dou E2 at E1 equal to E1 bar equal to 1 by omega 2 at E2 bar dou omega 2 E2 by dou E2 at E2 equal to E2 bar. Now this takes the form dou by dou E1, this is E1, dou by dou E1 of log of omega 1 E1 at E1 equal to E1 bar. Means this differentiation is done at E1 equal to E1 bar is equal to dou by dou E2 of log of omega 2 E2 when this differentiation is done at E2 equal to E2 bar. Means we can write this differentiation is at E1 equal to E1 bar and this differentiation is at E2 equal to E2 bar. Let's denote the quantity on the left hand side as beta 1 and that on the right hand side as beta 2. And so we find that when beta 1 is equal to beta 2, the system reaches equilibrium. So remember, we had two systems, A1 and A2. They were separated, and initially energy exchange was not possible, particle exchange was not possible, and volume exchange is also not possible. When we allowed the energy exchange to take place, keeping volume fixed and number of particles fixed, means exchange of particles is not allowed and volume change is also not allowed. Only energy exchange was allowed. Then we find that the composite system comes in equilibrium when beta 1 is equal to beta 2, where beta, we can see, is derivative of log of omega, which is function of, in general, N, V and E with respect to the energy E, when E is equal to E bar, that is for the equilibrium state. So dou by dou E1 of log omega 1 at E1 equal to E1 bar is equal to dou by dou E2 of log omega 2 at E2 equal to E2 bar is now the condition that the system reaches in equilibrium. So we reach a conclusion that when two systems are put in contact, the exchange of energy continues until the statistical parameter beta reaches a common value. As we know that when we allow two systems to exchange energy, when the equilibrium is reached, we call it thermal equilibrium. So these systems A1 and A2 have reached thermal equilibrium when this condition is satisfied. So as the system has reached thermal equilibrium, it is obvious that beta is related to the thermal temperature T of the system. So obviously, we understand that temperature of the system T must be somehow related to this quantity beta, whatever it is. We will find out what beta is at a later stage. But what is obvious is, in order that two systems are in thermal equilibrium, beta 1 must be equal to beta 2, where beta is defined by this equation. Let's stop it here for the first day. We'll take up other applications of this omega in the next lecture.